Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The 1965 collection titled Quantum, Electrodynamics, compiling Shinichiro Tomonaga's pivotal papers and his Nobel lecture, represents a profound intellectual achievement from a period of intense theoretical development and global isolation. The work stands as a testament to a uniquely powerful and rigorous approach to resolving the deep inconsistencies between quantum mechanics and special relativity. This essay undertakes a direct and systematic evaluation of the central claims, logical structures, and conceptual frameworks presented within this collection. The analysis will proceed through the core sections of Tomonaga's argument, from his foundational reformulation of quantum dynamics to a sophisticated resolution of the infinities that plagued the theory, assessing each component for its internal coherence, physical justification, and lasting contribution to the edifice of modern physics. Section 1: The relativistically invariant formulation and super-many-time theory. Tomonaga's work commences with a direct confrontation with the foundational challenge of reconciling quantum theory's single, universal time parameter with the framework of special relativity, where time is a local coordinate dependent on the observer's frame of reference. The initial papers in the collection present a radical and elegant solution to super-many-time formalism. The central claim here is that a consistent relativistic quantum theory can be constructed by associating an independent time variable with each point in three-dimensional space. This conceptual leap transforms the state of a quantum system from being defined at a single instant of universal time to being defined on a three-dimensional space-like surface, which is a surface where any two points have a separation such that a light signal cannot connect them. The physical state vector, conventionally written as psi of t, becomes a functional psi of sigma, dependent on the entire shape of this surface sigma. The evaluation of this claim hinges on its logical power to circumvent the problem of assigning a preferential time coordinate by treating all points on the spacelike surface as copresent. The formulation achieves a manifest Lorentz covariance in its structure. The methodology employed is a generalization of the canonical formalism of classical mechanics and its quantum analog. Tomonaga's argument is that the Schrödinger equation, which describes the evolution of a state vector with respect to a single time variable, is a special case, a more general evolution. This more fundamental evolution proceeds from one spacelike surface sigma1 to another, infinitesimally deformed surface sigma2. The brilliance of this claim lies in its preservation of the core structure of Hamiltonian dynamics while elevating it to a fully relativistic context. The evidence provided is the successful construction of a mathematical framework that accommodates this idea, a framework that remains consistent and yields familiar results in the non-relativistic limit. The argument is persuasive because it recasts the problem from an impasse of conflicting principles into a question of finding the correct mathematical generalization. Section 2: The Tomonaga-Schwinger equation as the engine of dynamics. Building upon the super-many-time concept, the collection introduces its central dynamical equation, a cornerstone of the entire edifice. This equation, which has come to be known as the Tomonaga-Schwinger equation, makes the profound claim that the evolution of the quantum state functional is governed by the local properties of the interaction. Specifically, it asserts that the change in the state functional psi of a surface sigma, when the surface is infinitesimally deformed at a spacetime point x, is determined by the interaction Hamiltonian density at that very point. The equation is expressed using a functional derivative, a sophisticated mathematical tool that captures how a functional changes in response to a localized change in its argument function. In spoken form, the equation states the functional derivative of the state functional psi with respect to the spacelike surface sigma at a point x, multiplied by the imaginary unit I and the reduced Planck constant h bar is equal to the interaction Hamiltonian density operator at X acting on the state functional psi. The evaluation of this claim reveals its deep physical and mathematical elegance. It proposes that causality is perfectly encoded within the theory. A change in the field configuration at a point X only affects the state's evolution in its future light cone, as propagated through the deformation of the space-like surface. The methodology is one of direct generalization. Tomonaga takes the standard Schrödinger equation in the interaction picture, where the time derivative of the state is governed by the interaction, Hamiltonian, and promotes the ordinary derivative to a functional derivative and the single time parameter to the entire space-like surface. The internal coherence of the argument is exceptionally strong. It provides a differential equation for the dynamics of the state functional, allowing, in principle, for the calculation of the system's state on any future surface given its state on a past one. The framework's power rests on its ability to handle a continuous infinity of degrees of freedom in a quantum field in a way that respects relativity at every step. The claim is that this single equation contains the complete dynamical information of an interacting quantum field theory. Section 3. The perturbative expansion and the emergence of divergences. Having established the general formalism, the papers within Tomonaga's collection proceed to the practical matter of extracting physical predictions. The central argument in this section is that the Tomonaga-Schwinger equation can be solved using a perturbative series expansion, a technique familiar from standard quantum mechanics. The state functional at a later surface, sigma, is expressed as a power series in the coupling constant, typically the fine structure constant for electromagnetism, acting on the state functional at an earlier surface sigma naught. Each term in this series corresponds to a more complex sequence of interactions. Tomonaga's presentation meticulously details the derivation of these terms, showing how they correspond to the emission and absorption of virtual particles. The critical evaluation of this section focuses on the consequences of this expansion. The claim that the theory is calculable via perturbation theory is immediately met with a severe challenge. The individual terms in the series, when calculated, yield infinite results. These divergences arise from integrals over the momenta of virtual particles that extend to infinity. Tomonaga's analysis of this problem is methodical and unflinching. He identifies specific physical processes responsible for these infinities, most notably the interaction of an electron with its own emitted and reabsorbed electromagnetic field, leading to an infinite self-energy and the creation and annihilation of virtual electron-positron pairs in the vacuum, leading to an infinite vacuum polarization. The intellectual honesty of his argument is a key feature. He presents the infinities as a direct mathematical consequence of the theory's fundamental postulates. His assessment at this stage is that the theory, as it stands, is incomplete. It generates unambiguous mathematical procedures that lead to physically nonsensical, infinite answers for measurable quantities like the mass of an electron or the strength of its charge. His claim becomes a diagnostic one. Formalism is correct, but its naive application reveals a deep structural issue that must be resolved. Section 4. The subtraction procedure and the logic of renormalization. The intellectual climax of Tomonaga's work, as presented in the collection, is his resolution of the problem of infinities through the method of renormalization. The central and most audacious claim of this section is that the calculated infinities be systematically and consistently removed from the theory by absorbing them into a redefinition of the fundamental parameters, the Lagrangian, specifically the mass and charge of the electron. The methodology he presents is a form of subtraction. He argues that the mass term that appears in the initial equations, the so-called bare mass, is a purely theoretical construct and is unobservable. The physically observed mass is the result of the bare mass plus the infinite self-energy corrections. His argument proceeds by postulating that this physically observed mass is, of course, finite, therefore The infinite self-energy must be precisely cancelled by an opposing infinity in the bare mass. The same logic is applied to the electric charge. The bare charge is modified by vacuum polarization effects, and only the resulting dressed or physical charge is a measurable quantity. In evaluating this claim, one must appreciate its profound philosophical shift. Tomonaga is asserting that the initial parameters of the theory are without direct physical meaning. Meaning resides only in the composite, experimentally accessible quantities that emerge after all interactions are accounted for. The evidence for the validity of this procedure is its success. By systematically rewriting the theory in terms of the physical mass and charge from the outset, all the infinities that appear in the perturbative calculations can be made to cancel each other out, term by term, to any order in the expansion. The resulting theory makes finite, and remarkably accurate, predictions for physical observables like the Lamb shift and the anomalous magnetic moment of the electron. The internal logic of the subtraction method is delicate, but coherent. It is a reorganization of the perturbative series, separating out the divergent parts and grouping them together in a way that corresponds precisely to the redefinition of physical constants. This is a claim of profound consequence. The infinities are artifacts of an improper separation of the particle from its own field, and the renormalization procedure is the mathematical embodiment of correcting this conceptual error. The intellectual wit here is subtle. The theory's most glaring flaw becomes the key to its ultimate predictive power, a paradox resolved by redefining what the theory is fundamentally about. Section 5. The covariant, perturbation theory, and equivalence, a crucial portion of Tomonaga's collected works, demonstrates the practical implementation and formal elegance of his ideas. This involves the development of a manifestly covariant perturbation theory, a step that was essential for proving the consistency of the renormalization program to all orders. The principal claim here is that the time-ordered product of operators, a central feature of interaction picture calculations, can be formulated in a way that is explicitly independent of the choice of reference frame. Tomonaga's method for achieving this involves a careful handling of the operator algebra and the integration over four-dimensional spacetime. His formulation provides a clear, step-by-step prescription for calculating any scattering process. The evaluation of this section must acknowledge its pivotal role in bridging the gap between his abstract formalism and the work of other physicists. While his supermagnetime theory provided the conceptual foundation, it was this detailed development of the calculational techniques that allowed for direct comparison and verification. The methodology involved expressing this matrix, which connects initial and final states in a scattering experiment, as a time-ordered exponential of the integral of the interaction Hamiltonian density over all spacetime. The subsequent expansion of this exponential generates all the terms of the perturbation series. Crucially, Tomonaga's work showed how to handle the commutators of field operators at different spacetime points, ensuring that the calculations respected causality and Lorentz invariance. The successful demonstration of this covariant calculational scheme was the final piece of evidence needed to solidify his theory. It provided the machinery that Freeman Dyson would later use to prove the equivalence of Tomonaga's operator-based formalism with the seemingly disparate pathetical approach of Richard Feynman. Therefore, the claim evaluated in this section is one of completeness and utility. The abstract beauty of the Tomonaga-Schwinger equation is matched by a concrete and powerful calculational apparatus that is both internally consistent and externally verifiable. It transformed a philosophical resolution into a working tool for theoretical physics. Section 6. The Nobel Lecture as a narrative of discovery. The inclusion of Tomonaga's 1965 Nobel Lecture, Development of Quantum Electrodynamics, provides a unique opportunity for evaluation, as it presents the author's own retrospective assessment of his claims. Here, the central claim is a narrative one that is isolated yet persistent development. In wartime Japan followed a logical and self-contained path toward the solution of QED. He frames his work as a direct and conservative generalization of the principles of quantum mechanics, driven by the necessity of relativistic invariance. In his telling, the supermannitime theory was the only plausible way to maintain the Hamiltonian Schrödinger picture. He recounts the intellectual journey with a notable humility, describing the painstaking calculations and the slow dawning of the renormalization idea. An evaluation of the lecture reveals a masterful piece of scientific rhetoric. Tomonaga emphasizes the continuity of his thought process, presenting the subtraction of infinities not as a radical, ad hoc trick, but as the logical conclusion of taking the interaction picture to its relativistic limit. The evidence he provides is the story itself, a compelling account of confronting a problem, developing a new language to describe it, and following that language to its ultimate conclusion. The lecture serves to solidify the philosophical underpinnings of his technical papers. It makes the case that renormalization is a physically motivated and necessary feature of any interacting quantum field theory, a consequence of the inseparable nature of particles and their fields. There is a quiet intellectual irony in his description of learning. After the war, that Julian Schwinger in the United States had independently developed a very similar formalism. This historical detail, presented matter-of-factly, reinforces the perceived inevitability and correctness of the approach. The lecture's claim is that the path of discovery was dictated by the internal logic of physics itself, a path that different minds, working in isolation, and did. In conclusion, the body of work encapsulated in the 1965 collection Quantum Electrodynamics presents a remarkably complete and self-contained argument for a consistent, predictive theory of quantum electrodynamics, in evaluation of its internal claims, section by section, reveals a structure of impeccable logical progression. It begins with a fundamental reconceptualization of time in quantum theory, a necessary step to ensure relativistic consistency. From this foundation, it derives a new equation of motion, the Tomonaga-Schwinger equation, which elegantly encodes causality and Lorentz invariance. When confronted with the infinities that arise from this formalism, the work provides a sophisticated and ultimately powerful resolution through the program of renormalization, a procedure justified by a profound reinterpretation of the physical meaning of the theory's parameters. The claims made at each stage are bold, yet they follow from a rigorous application of established principles to a new and more complex domain. Tomonaga's formulation, with its focus on the evolution of the state vector on a deformable space-like surface, offers a physically intuitive and mathematically rigorous picture of quantum dynamics. Its enduring significance lies not only in its historical role in the creation of modern QED but also in the clarity and power of its core concepts, which continue to provide a fundamental perspective on the nature of interacting quantum fields. The collection stands as a monument to the power of sustained, focused inquiry and the triumph of logical coherence in the face of apparent paradox.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.